Alright, we are continuing to look at average atomic mass problems, starting with number 4, which says naturally occurring chlorine that is put in pools is 75.53% chlorine 35 with a given mass, and 24.47% chlorine 37 with a given mass. Calculate the average atomic mass. So we're going to organize our information. We could organize it into a table like we've been doing, but we don't necessarily need to. We just need to make sure that it's clear where our work is. So I'm going to model a different method for showing your work here. We'll write out our two isotopes at the top of our page. So let's start with chlorine 35. And then beneath that isotope, I'm going to list my mass and multiply it by my percent abundance as a decimal. So we'll do, in parentheses, 34.969. And we'll go ahead and multiply it by its percent abundance as a decimal value. So let's go ahead and do our jumps here. Our decimal version of 75.53% is going to be 0.7553. And then we'll close the parentheses. So this right here is for chlorine 35. And then we'll do the same thing for the other isotope, which is chlorine 37. We'll do it over here, and then we'll just add these two things together. So this is a way to show all your work without the table format. So this is for chlorine 37. And we'll do the same thing. We'll pick its mass up, 36.966. And then we're going to multiply that by its percent abundance, which for chlorine 37 is 24.47%. Let's convert that to a decimal, move that decimal point 2 times. So as a decimal, that's 0.2447. Close that set of parentheses, and that's our work for chlorine 37. Okay, so now we still need to do our calculation the same way, but we're already showing that we're adding these two things up. So all I'm going to do here is I'm going to multiply this out, write my answer, multiply my chlorine 37 data out, write my answer, and then I will show my final answer when I add those two numbers up. So let's go back to our calculator, clear some things out. So I'm going to start with 34.969. These are such long numbers in these problems. That's the trickiest part probably, is making sure we're typing the numbers correctly. 0.7553. And that gives me a mass contribution of 26.412, and I'm not going to write the rest of this out because I will just go back and select that value in my calculator, but I'm not going to write the whole thing out right now. So that's my mass contribution for chlorine 35. And then of course we need to do the same thing for chlorine 37. Multiply those values out. 36.966 times 0.2447. And there's my mass contribution for chlorine 37, which is 9.04558. But we don't need to write all those digits out because now we're just going to add these two things together to get our final answer. So 26.412 plus 9.04558 is going to give us a final answer. We'll select that one, plus our second value, gives us a final answer of 35.4576, and that's probably enough digits, but let's go back and check how many significant figures our answer should have. Our final answer should have the same number of significant figures as our mass values, and each of our mass values has 5 significant figures. So our answer should also have 5 significant figures. Maybe I'll write out one more digit, that next 6 that's over in my answer. And now I'm going to go back and round to 1, 2, 3, 4, 5 significant digits, and then we'll look at the next digit over. That 6 tells us the 7 will round up to an 8. So the answer that we should report is 35.458. And of course our units are AMUs, just like they are in the problem. AMU. There is our final answer. To check to make sure it's reasonable, we want to make sure it's between both of our given mass values. It's between 36.996 and 34.969. It is indeed between those two values, so that is a reasonable answer to this problem. Number 5 says, why is the mass in AMU of a carbon atom reported as 12.011 on the periodic table of elements? What kind of average is average atomic mass? Okay, so this question is just asking us to describe what is a weighted average. The type of average, of course, is a weighted average. Average atomic mass is a weighted average. Weighted. Okay, so this problem is just asking us to describe that why the average atomic mass of carbon is so close to 12, even though there are several isotopes of carbon. We have carbon 12, carbon 13, and carbon 14 are all fairly common isotopes. We can isolate those in nature. So why is the mass so close to carbon 12? Well, that has to do with abundance. Out of these three isotopes of carbon, isotope 1, isotope 2, and isotope 3, carbon 12 is by far the most abundant isotope. It is the most abundant. Most abundant. So the mass is weighted much more towards carbon 12 than it is towards the other two isotopes. So carbon 12, because of its high abundance, the average atomic mass on the periodic table demonstrates that with an average atomic mass that is very, very close to 12, even though there are other isotopes of carbon that have heavier masses. But carbon 12 is the most abundant isotope. It has the greatest percent abundance, and therefore the mass is very, very close to 12, even though there are other isotopes of carbon. And that all comes back to that weighted average, the idea that each isotope's mass does not count equally. It is weighted based on its percent abundance. Last but not least, number 6 says magnesium has 3 naturally occurring isotopes, and then it gives us a whole bunch of data, since there are 3 isotopes, I'm going to go ahead and put this in a table format. So we're going to list out our isotopes. We'll put our abundance, and then we'll put our mass values. Fill in our table. We have magnesium 24 with that percent abundance, Mg24, which is 78.7% abundant. We have magnesium 25, list that as our next one, Mg25, which has an abundance of 10.13%. And then we have Mg26, our last isotope, which has an abundance of 11.7%. Now we just need to fill in our mass column. The average atomic mass of the 3 isotopes is 24.3050. Oh, so this is a little bit of a different problem. It gives us the average atomic mass. So it gives us the weighted average of these 3 isotopes. So when we add up our mass contributions, this is the number that we should find. When we add up all these mass contributions, we should get this value of 24.3050. So we must be looking for a different piece of information in this problem. Alright, so let's keep reading to figure out what we're looking for. Okay, it says, if the average atomic mass of magnesium 25 is this number, so that gives us the mass of magnesium 25, so that would be the second one, is 24.98584. And mass of magnesium 26 is 25.98259. It says, calculate the actual atomic mass of magnesium 24. So we don't know what this value is, and so we need to solve for that value given the final average atomic mass of magnesium, which we were given in the problem. So this problem's a little bit different. We're going to have to do some algebra to solve this. When we don't know something in math, we substitute in a variable. And people generally like to choose x, so we'll go ahead and use that. So we don't know the actual mass of magnesium 24, so we're going to substitute in a variable x. And we're going to leave x there and simplify our equation. And so we'll calculate the mass contribution for magnesium 25 and for magnesium 26, but then we will leave x in for magnesium 24 when we calculate that mass contribution. So we'll move that decimal point 2 times, just like we always would, but we can't multiply by x. We can just write it out as an algebra expression. So it's 0.787. We multiply these two together times x. So we'll just leave it unsimplified, 0.787x. That's our mass contribution for magnesium 24. Now we can calculate the mass contribution for magnesium 25 because we have our percent abundance and our mass. So we'll do 0.1013 times 24.98, it's a long number, 584. Okay, so our mass contribution for magnesium 25 is 2.5310, and I'm going to round that 6 to a 7. Kept a bunch of significant figures there. I'd recommend keeping at least as many as are in your problem. So we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. I actually didn't keep enough there, so I won't round at that 7. I'll keep some more digits, 0, 6, 5, and then I'll round the 5 up to a 6. So I kept plenty of sig figs there. Now let's do our mass contribution for magnesium 26. Move the decimal point twice before we multiply. So convert to a decimal, 0.11. Alright, so 0.117 times our mass of 25.98259. And that gives us a mass contribution for magnesium 26 of 3.03. 996, and then we'll keep one more, 3. All right. Okay, so now we know that to get our average atomic mass, normally what we do is add up all of our mass contributions, and it would be our average atomic mass. So this time we're just working a little bit in reverse. We're going to have to solve algebraically to find our solution for our variable x. So, we're running out of some room here. So let's pause and move this up for a second. Okay, now that we have some room, let's set up our algebra problem. Alright, so we have 0.787x plus 2.5310656 plus 3.039963. All that added together equals 24.3050. Alright, So when we do algebra, the first thing we usually want to do is see if we can combine some like terms. So our two values right here, these are like terms, so we can combine those. So we'll do 2.53 plus our 3.03. And if we combine those, we can simplify a little bit by combining these like terms, and we got 5.5710286. So I know writing out these numbers is kind of a pain, and you might not be used to seeing these big numbers in algebra class, but it's okay. It's not really any different. We just have to spend more time writing. So now we simplified to 0.787x plus 5.5710286 equals 24.3050. Now the next thing we can do is we want to separate our x terms from our terms without x's. So we're adding 5.5710286. We want to move that to the other side. So we want to do the opposite. We want to subtract it. So 5.5710286. And if we do something on one side, we're also going to do it on the other side. Minus 5.5710286. So when we do that, these terms will cancel out, and we'll be left with just this part left, the 0.787x on our left-hand side, and that will equal 24.3050. We'll come over to our calculator, 24.3050 minus our 5.5710. And when we subtract these two values, when we do the subtraction for these two values, it leaves us with 18.73397. And then, last but not least, to isolate our x term, we're multiplying 0.787 times x, so the opposite of multiplication is division. So we need to divide by that term, that 0.787. If we do it on one side, we do it on the other side as well, divided by 0.787. And then, of course, these will cancel out. Now we're just left with x on our left-hand side. X equals whatever 18.73 divided by 0.787 is. So 18.73 divided by 0.787. And that gives us 23.80428. We're kind of running out of room here. So we need to look at our significant figures. Our mass values were given with a lot of significant figures, actually. 1, 2, 3, 4, 5, 6, 7 sig figs over here. Well, let's look at the value 1, 2, 3, 4, 5, 6 significant figures over here in our other mass value, our average atomic mass. We'll round our answer to 6 significant figures as well. We'll keep 1, 2, 3, 4, 5, 6. And after that 2 was an 8. We'll look at that 8, and that makes the 2 round up. We've kind of run out of room here, so I'm going to write our final answer on the far left side. So that would be 23.804. And then we decided that 2 would round up to a 3 because 8 is larger than 5. And that is in AMUs. And that is the mass of magnesium-24. So we want to write that because it's not an average atomic mass. It's the mass of Mg24. And there is our final answer. That was a whole lot of work. That's a little bit more challenging of a problem, but really we just had to use our algebra skills and apply it to a word problem here.